Here are some solutions to the 1.4 tangent and velocity problem activity. The first page of this activity asks you to calculate the slope of 4 secant lines to the function x minus 1 quantity squared. I've drawn in those 4 secant lines for you and color-coded them. We're going to find the slope together here of the line that is colored in black. Let me make sure my color coding is going to be good. Okay, so the slope of that secant line is again the change in y, which is 1 minus 0, divided by the change in x, which is 2 minus 1, and that is 1 divided by 1, or 1. Okay, I've gone ahead then and calculated the slopes of those other 3 secant lines. The line in red between 1, 0 and 3/2 f of 3/2, that was calculated in the lecture portion of this section, has slope 1/2. The line in orange between 1, 0 and 5/4 f of 5/4 has slope 1/4. And the line in purple between 1, 0 and 11/10 f of 11/10 is calculated here and has slope 1/10. So let's see, what can we learn from those 4 secant lines? Well, the first thing is we can ask about maybe another secant line. What if we wanted to calculate the slope of the secant line between 1, 0 and 101/100ths and f of 101/100ths? Well, if we look at what's happened in the first 4 examples, we see here in number 2 that we went from an x value of 1 to an x value of 3/2, which is a change of 1/2, and that happens to be the slope of the secant line. Looks like the same thing happens here in number 3 from 1 to 5/4, which is a change of 1/4 and a change of 1/10. So here we would be looking at a change from 1 to 101/100ths of 1/100th, and it is true that the slope of this secant line would be 1/100th. Okay, now that is a coincidence based on this function. That's not always going to work that way, so don't take that as an assumption. We will need to calculate such slopes manually as we move forward, but we can see a pattern in this case. So what else can we learn from the slopes of these secant lines? Well, what are they starting to look more and more like as the x value moves down the curve towards the point 1, 0? They are looking more and more like what is called a tangent line. So a tangent line is a line through a point on a curve in the same direction as the curve or function. So here I've sketched the tangent line to our curve at 1, 0. And if we go back up, we can see that our secant lines are starting to look more and more like that tangent line. And what's happening to the slopes of those secant lines? They start at 1, they go to 1/2, they go to 1/4, they go to 1/10, they go to 1/100th. And we see our tangent line here, and what do we know about the slope of horizontal lines? We know that the slope here of this tangent line is equal to 0. And does that make sense? How could we have used our work above to find this slope? Well, we could use our work above by noticing that the slopes of all of these secant lines are decreasing. They're getting smaller and smaller, and they're actually approaching 0. So the slopes of our secant lines approach, spelled incorrectly, the slope of the tangent line. Okay, great. So this is out of context, but let's see what happens if we put this in a little bit of context on the next page. Okay, so we're going to look at the context being velocity. So we've been given the position function of a ball. So it's thrown into the air. After some number of seconds, you can find its height as 80t minus 16t squared, where t is in seconds. And the first thing we're asked to do is find the slope of the secant line from 1h of 1 to 2h of 2, and to think about what the units are for this slope. Okay, so I guess to do that, we need to do a little bit of calculation here about this function. We need to know what h of 1 is. H of 1 is 80 times 1 minus 16 times 1 squared. And that is 80 minus 16, or 64. We also need to know what h of 2 is. That's 80 times 2 minus 16 times 2 squared, which is 160 minus 16 times 4. 160 minus 64. So that is 96. Okay, so now the slope of this line then is going to look like this. It's going to look like h of 2 minus h of 1 divided by 2 minus 1. And that slope then is h of 2, which is 96, minus h of 1, which is 64, divided by 1, or 32. The last part of this question asks us what the units are for that slope. Well, let's see. Let's add some units to what we've done. So t, the input to this function, is given in seconds, and the output is given in feet. So that means this 64 is given to us in feet. It's an output of the function. This 96 is given to us in feet, and the 1 and the 2 are measured in seconds. So it looks like we have feet in the numerator and seconds in the denominator. And so this is 32 feet per second. Okay, so I'll bring that slope down here to number 2. Number 2 asks you to calculate a whole bunch of these things. I've done that here for you and color-coded the work in number 2. We said if we shrink the time interval a little bit to t equals 1 to t equals 3 halves, we get a slope of 40 feet per second. T equals 1 to t equals 5 fourths, we get a slope of 44 feet per second. T equals 1 to t equals 11 tenths, we get a slope of 46 and 2/5 feet per second. Okay, so the slope of the tangent line at t equals 1 to our curve is an instantaneous velocity of the ball at t equals 1. So it's the velocity of ball at that exact time, not an average velocity, which is what we've just calculated above. But what we also have calculated above are slopes of secant lines. And so our question is, do our slopes of secant lines, are they clearly approaching something that would allow us to determine what the slope of that tangent line is? Here we see our secant line slopes increasing from 32 to 40 to 44 to 46 and 2/5. I don't know what's going to happen next. I can't be certain that this is getting closer to 47 or 48 or 50. It was pretty clear in the previous example that those slopes of secant lines were getting closer to 0, but it's not clear here. So I cannot make a prediction. I cannot predict instantaneous So what would I need to do? I'd need to do some calculations over smaller time intervals. Maybe time intervals like t equals 1 to t equals 101 100ths. Or maybe t equals 1 to t equals 1001 1,000ths. And I would keep doing this until it became a clear pattern as to what number those slopes of secant lines were approaching, and then hence that would give us the slope of the tangent line and the instantaneous velocity of the ball at that point.